Hello everyone, my name is Jayant Anand and I am a student at Vellore Institute of Technology in Vellore campus. I am pursuing a degree in Electronics and Communication Engineering with specialization in Biomedical Engineering. And today we shall be learning about the concept of laser physics and engineering physics. So, light sources. When we think of lasers, we automatically assume it to be a light source, which is true. And a light source converts an electrical signal into an optical signal. This can be classified into three types: incandescent lamp, light emitting diode, lasers. Incandescent lamps are also known as conventional light sources, and it is a continuous spectra, or it is continuous in nature, that is neither monochromatic nor coherent. The light emitting diode, or also known as an LED, unlike an incandescent lamp, is discrete. But while it is monochromatic, it is not coherent. So incandescent lamp is neither monochromatic nor coherent. LEDs are monochromatic but not coherent. Lasers or light amplification due to stimulated emission of radiation. This is the full form of lasers, which is important as we are studying the unit of lasers. So these are also discrete and monochromatic, but they are also coherent. So therefore we can say that conventional light sources are continuous, non-monochromatic and non-coherent. LEDs are discrete, monochromatic and non-coherent, and lasers are discrete, monochromatic as well as coherent. Now, there are certain laser characteristics you have to understand. Now, the first is high directionality. So as we know, conventional light sources, they emit light in all directions, and we therefore have to have an aperture where the light is concentrated into a smaller area for us to get a beam. Lasers, on the other hand, are highly directional and are emitted in one direction. So the directionality of lasers is expressed in terms of a quantity called full angle beam divergence. So this quantity is defined as twice the angle that the outer edge of the beam makes with the axis of the beam. So if we take a beam, that outer edge with respect to the axis forms an angle. The double of that angle is known as the full angle beam divergence. So here we have a laser. Here is the outer edge and here is the axis. I naught being the axis here, I naught by E being the outer edge. And the angle formed here is theta by 2 because theta is the full angle beam divergence. And half of that angle is basically the angle between the outer edge and the axis. So therefore it is theta by 2. D here is the aperture diameter, and then we can also say that d square, or the square of the aperture diameter divided by the wavelength, is known as Rayleigh range, and the angular spread delta theta of the far field is related to the aperture diameter as delta theta equals to lambda by d, where lambda is the wavelength. For a typical laser, the beam divergence is around 0.01 milliradian. This means that the beam would spread less than 0.01 millimeter for 1 meter. So the beam divergence it shows is very small compared to the naked eye that which can perceive it. So 0.01 of a milliradian. Milli itself is 10 power minus 3. 0.01 is of that would become 10 power minus 5 radian. So it tells that for an area of 1 meter, the beam will occupy not even 0.01 millimeter of that. Then lasers also are said to have a high intensity. We've learned as kids from our parents and teachers that we should never look directly into a laser beam. This is because they have a high intensity. Now lasers, because they give out their light in a narrow region, its energy is also concentrated into the same region. So it has such a high intensity that a single watt laser is much more intense than a bulb that is 100 times more powerful. A bulb of 100 watts pales in comparison to a single watt laser. This intensity is expressed in terms of photons per second, where it would be around 10 power 16 to 10 power 28. The output power of a laser can vary, where in a continuous laser the power is expressed in milliwatts, and in a pulsed range it is expressed in terms of gigawatt, which is 10 power minus 3 to 10 power 9 watt. Next is a high degree of monochromaticity. So here we can say that mono means one, chrome means color. So therefore it exhibits a concept where it will only give out one color. And lasers are much more monochromatic than any other conventional light source, but absolute monochromatism is impossible. So it is not perfectly monochromatic due to the uncertainty principle between energy and time. Just like how we've learned in Heisenberg's uncertainty relation that an electron in orbit cannot have its position and momentum simultaneously determined. Similarly, here there is a relation with respect to energy and time, different parameters. There is another quantity known as the degree of non-monochromaticity, which is the ratio of change in frequency with respect to threshold frequency. The change in frequency is roughly around 100 to 1000 hertz, and the change in wavelength is roughly between 10 power minus 8 to 10 power minus 2 angstrom. And while wavelength is not directly part of the equation, we can use the wavelength to determine frequency if it is not given, and use that frequency in the equation. Now, lasers are also said to be highly coherent. That is, they have the same phase or constant phase difference. The light coming out of a laser is highly ordered, and therefore it also results in a large spatial concentration. Now, what is coherence? Coherence basically it involves the concept where light which has smaller wave fronts, they move around in a random manner, and in so they kind of reinforce or cancel each other. So the wavefront that is produced would vary in terms of position, known as spatial coherence, and with respect to time, known as temporal coherence. So here we have a light source, and we have 2 points. One is at a given point in this way in the wavefront, and another is in the similar position of the same wavefront, but at a different time interval. This is an example of temporal coherence because it involves 2 points in the same two points in a same position but different time interval. Then we have these 2 points on the same time interval but different positions of different wavefronts. So because it varies from point to point here, this is known as spatial coherence. So temporal coherence or transverse coherence is the correlation between the field at a point and the field at the same point at a later time. Like I told, it varies from time to time and the positions are the same. So therefore, if the phase difference between the two fields remains constant during the period of observation, then the light source is termed as temporally coherent. Next, we come to spatial coherence. So, two fields at two different points on a wavefront of a given electromagnetic wave are said to be space coherent if they preserve a constant phase difference over any period of time t. So, the two fields here at two different points, we saw there are two different points of two different wavelengths, but of similar time interval. So if they are, regardless of that time, they will have a constant phase difference, and in that case they are said to be spatially coherent. And here they have taken an example of when you have a point source at the focus of a convex lens, where the radiation transmitted by it will consist of nearly plane waves which are spatially coherent. Now the difference between temporal and spatial coherence is the temporal coherence is with respect to a single beam of light, while spatial coherence is usually with respect to two or more beams of light. Now coherence length and coherence time. Now this is a very easy concept because as we know, we can see here that there is a sinusoidal curve that is there, a uniform behavior of the waves. So the time interval where the sinusoidal behavior remains is known as coherence time, and the corresponding length of it is known as coherence length. And we can see here that the coherence length is related to the coherence time such that the coherence length is the product of coherence time with respect to speed of light, c. And after the coherence time, there is no correlation between the phase of the waves. Now we have absorption and emission, which we have known as kids, because absorption refers to taking in something, emission relates to releasing something. So here absorption, it takes in energy, emission gives out energy. So here we have two energy states, E1 and E2, and the difference in energy delta E is E2 minus E1, which equals to h nu. And of course they will correspond to different electronic configurations. And we can see here that the difference in energy from the higher state to the lower state is directly related to the frequency of the absorbed or emitted radiation. So in absorption, we can see that there is a particle or a photon, here in this case, a photon at a lower energy state, which when we provide energy moves to a higher energy state. So this is a classic example of absorption. And keep in mind, absorption is always stimulated. Spontaneous emission. Now emission is of two types, spontaneous and stimulated. Spontaneous in this case means the photon from a higher state moves to a lower state and gives out energy. Basically, in moving from a higher state to a lower state, it releases energy. And therefore, it is a random nature from a large number of atoms, resulting in incoherent radiation. Then you have stimulated emission. Stimulated emission is similar to spontaneous emission in the sense that the photon moves from a higher to lower state, but we have to provide energy to the photon for it to release energy. That is, in spontaneous emission, it is simply moving from higher to lower state and releasing energy. Here it is moving from higher to lower state by providing energy so that it can eventually release energy. And nature as a whole will only understand two processes: stimulated absorption, stimulated emission. That's it. Spontaneous emission is an artifact and actually is a special type of random stimulated emission due to 0-point energy of vacuum. Now, the light associated with the stimulating and stimulated photon is in phase and has the same polarization. This is known as coherent radiation. Now, when an atom is stimulated to emit light energy by an incident wave, the liberated energy can add to the wave in a constructive manner, providing amplification. So, when an atom emits light energy through emission, so this energy is basically transferred to other atoms, which in turn will release more energy, and thus it propagates, known as amplification. Now we have Einstein's relation. Now we've already learned about the rates of these three processes: absorption, spontaneous emission, stimulated emission. Now, as a whole, we already know that we are assuming that the whole system is in thermal equilibrium. For Einstein's relation, we also have to understand that the rate of upward transition is equal to the rate of downward transition. Just like how we say that if it takes, assuming if 2 points A and B are present, and we have to go from point A to point B, the distance is 50 kilometers and we are traveling at 10 kilometers per hour. So it will take us 5 hours to go from point A to point B. Similarly, to go from point B to point A, we are still covering the same distance, we are still moving the same speed, and therefore we will take 5 hours again. So therefore the rates are still the same. Just like that here, the time it takes for a photon to move from a lower state to a higher state will be the same time it takes to go from a higher state to a lower state. Now, this can be explained by Maxwell-Boltzmann's distribution. Now here Maxwell-Boltzmann's distribution states that n equals to g into exponential of minus e by kBt. T here is the temperature, kb is basically the Boltzmann constant, Maxwell-Boltzmann constant, E is the energy, and n here is the density of atoms in the energy level. Now G here is a degeneracy factor, because quantum mechanical states that have the same energy will be known as degenerate states. Now we take the ratio of the density of atoms. So n1 by n2 equals to g1 exponential of minus e1 by kBt whole divided by g2 exponential of minus e2 by kBt. which we simplify to get G1 by G2 exponential of h nu by kBt, because it will give us the difference in energy delta E, which is E2 minus E1, which is also equal to h nu. Now, the rate of upward transition is R1 to 2, the electron transition from lower to higher state. And it is directly proportional to the density of atoms in the first energy state. It is also directly proportional to rho v, which is the spectral energy density. And we can say that R12 is directly proportional to rho v n1 or equal to B12 rho v n1. Now, B12 is nothing but a proportionality constant known as Einstein's coefficient for absorption. Now, the average time an electron spends in an excited state before spontaneous emission takes place is known as spontaneous lifetime, or also known as tau to 1, the time from 2 to 1. Here, G21 equals to N2 into 1 by tau to 1, which equals to N2A to 1. Now, F21 equals to B21 N2 rho V. Like we know, we're just substituting that we're taking it from through emission, not absorption this time. And A21 and B21 are the corresponding Einstein coefficients. And B21 here would be Einstein's coefficient for emission rather than the coefficient of absorption. Same as with A21. Now R21 is nothing but G21 plus F21, which is nothing but A21 N2 plus B21 N2 rho V. And since we know that rate of upward transition is equal to rate of downward transition, we can substitute to equate. B12 N1 rho V equals to A21 N2 plus B21 N2 rho V. So by taking B12 N1 rho V to the LHS, to the RHS, and A21 N2 to the LHS, we can take rho V as common and equate it to get N2 A21 by N1 B12 minus N2 B21. Which on simplification we will get A21 by B21 divided by G1 B12 by G2 B21 exponential h nu by kBt whole minus 1. Because we are simply substituting the formula that we got for N1 by N2 into this. So from Planck's theory of black body radiation, we know that the spectral energy density equals to 8 pi h nu 3 n naught 3 by c cube into 1 by exponential of h nu by kBt minus 1, which we got from quantum mechanics as part of the Rayleigh-Jeans formation. Now we also know that B12 equals to G2 by G1 into B21 as part of the relation that we had just seen. Therefore, we can say that A21 by B21 equals to 8 pi h nu cube n naught cube by c cube. Basically, we just substitute and we get this answer. So hence, when degeneracies of the two levels are the same, B12 equals to B21. Einstein's coefficient for absorption equals to Einstein's coefficient of emission. The probability of the absorptions and stimulated emissions are also the same. And thus the stimulated emission rate by the spontaneous emission rate equals to B21 rho V by A21, which equals to 1 by exponential of h nu by kBt whole minus 1. So therefore, spontaneous emission is dominant for any system that is under thermal equilibrium. And here we have to understand that the rate of stimulated emission must be increased to a maximum extent so that we can obtain a coherent source. Otherwise, it will become incoherent. Now, the population density in the upper level has to be greater than the population density in the lower level. And when that condition is reached, this condition is known as population inversion. So here is a graph that has been plotted with energy in the y-axis and density of atoms on the x-axis. We've taken the density of atoms N1 and N2, energy is E1 and E2, and we plot a curve and we see that the curve represents the exponential function of minus E by kBt, and this is known as the normal thermal equilibrium distribution. The non-equilibrium distribution leading to population inversion is pretty much the similar way, except we are not plotting the same point. We are just getting the same curve that is present here. Now, there are certain methods by which population inversion can be achieved. So for first, it requires two mirrors, and in between there has to be an active medium that is placed, which can either be a solid, liquid, or a gas. But the thing is, you cannot achieve population inversion thermally by modifying the temperature or the thermal state of it. So therefore, there are certain methods that are there. One method of which is known as pumping. So there are multiple methods. The first is optical pumping. So here we take a xenon or krypton flash lamp used to provide light energy to the system, which is shown by an example in ruby laser. The second is a direct electron excitation through electrical discharge. So similar to electrical discharge, and it is used in gaseous ion lasers. Here the electrons are released from atoms due to high voltage electric discharge through a gas. In this case, the medium is ionized and population in higher level is increased. For example, an argon ion laser. The third is an inelastic atom-atom collision, which is done by pumping by electrical discharge again that provides the initial excitation which raises any atom to their excited state. So these will collide with another type of atoms and so on and so forth. An example here would be helium neon laser and helium cadmium laser. The fourth is by chemical reaction, where the molecules will undergo a chemical change and the product is in a molecule or atom that is in an excited state directly. And the fifth is of course by direct conversion, where we convert electrical energy into radiation. An example for chemical reaction would be hydrofluoric acid laser, and direct conversion would be semiconductor diode laser. So we have to understand there are three types of systems that we have to deal with: 2-level system, 3-level system, 4-level system. Now for a 2-level system, we cannot achieve population inversion no matter what we try, because B12 equals to B21. Rate of upward transition equals to rate of lower transition. Probability of both of them is the same. So at best, even when you pump it, you're going to get a 1:1 ratio on both sides, which will not fulfill the condition for population inversion. However, it can be achieved in 3 or 4 energy levels as well, because they contain a metastable state. Now, what is a metastable state? A metastable state is basically a state in which the electron or photon here, the atom in this case, sorry, the atom would spend an unusually large amount of time in that particular state compared to the rest of the states. So from this metastable state, we can say that the stimulated emission or lacing action will eventually take place. So here is an example of a 3-level laser. For example, a ruby laser. We have a ground state E0 and a second excited state in E2. So we can say here that E1 is your metastable state. So while after we pump from E0 to E2, there is a non-radiative fast transition from E2 to E1, where it stays in a metastable state before falling back to the ground state while releasing energy. Now in a 4-level laser, we have the ground state E0, the first excited state E1, and the third excited state E3. So which means the second excited state E2 will be the metastable state. So we pump from E0 to E3. We have a fast non-radiative transition to E2 where it stays in the metastable state. It releases energy after moving to E1. And then we also have another fast non-radiative transition back to E0, because it's a 4-level system and not a 3-level system. A common example of a 4-level laser would be a helium neon laser. Now the laser threshold condition. So here that if we differentiate the intensity with respect to Z, we get minus alpha I. Alpha here is the attenuation factor, and it is equal to C square by V square tau sp 8 pi n naught square whole into G nu of n1 minus n2. So G nu here is a broadening function, alpha is an attenuation factor, and all of this is equal to minus gamma, where gamma is the amplification factor or gain factor. So population inversion is a necessity for amplification to take place, and only when radiation can come when you have the amplifying medium placed in an optical resonator, which is a couple of mirrors that are facing each other directly. So here we have the two mirrors R1 and R2 separated by a distance d. We have the light that is passed here with an intensity I naught, which lands here at an intensity I naught e to the power omega minus alpha 1 d, where alpha 1 is the average loss or length due to all loss except reflectivity. So there is a loss in intensity that takes place naturally. And then it is reflected off and goes back to R1 at a different intensity, and then again reflected back off R1 to go to R2. So it keeps oscillating. But the losses have to be compensated by the gains. Only then the oscillation can be sustained. Otherwise, it would simply just go back and forth a couple of times and that would be it. So therefore, there has to be a minimum population inversion that has to be established for the losses to be overcome. So this is the condition that has to take place. R1, R2 e to the power 2 into gamma minus alpha 1 d has to be greater than or equal to 1. Only then the laser oscillations can begin. So if population inversion is increased, then your LHS, this side would obviously be greater than 1. That is needless to say. So the round trip gain has to be greater than the round trip loss. Like we told, the loss has to be compensated by the gain. So here, gamma has to be greater than or equal to alpha 1 minus 1 by 2d logarithm of R1, R2. Now we are about to discuss the three types of lasers that we will discuss. The first is the helium neon laser, the second is the carbon dioxide laser, and the third is the Nd:YAG laser. Now the helium neon laser was first developed by Ali Javan, W. Bennett, and D. Heriot in 1961. The operational wavelength is 632.8 nanometer because it shows the red portion of the visible spectrum. And we had already just discussed earlier that it is a 4-level laser scheme. And it is a gaseous laser that provides more direction and more monochromaticity than a solid state laser. However, its output is only moderate compared with that. The active mixture in a helium neon laser is a mixture of helium and neon gas in a 10:1 ratio based on atomic percentage. So this is an important thing because we have to use that active mixture for the working. So it is a mixture of helium and neon gas in a ratio of 10:1 respectively based on atomic percentage. Now, why is helium and neon used here? Here, neon is an active center for lasing action, and helium basically acts as a stimulator, just helping in the efficient excitation of neon atoms. Now, the construction of the helium neon laser is such that the discharge tube is of a length of 80 centimeter and with a diameter of 1.5 centimeter. The pumping is provided by creating a discharge by applying a voltage of almost 1 kilovolt through the anode and cathode of each end, and the current that is there present inside varies from between 5 to 100 milliamperes for continuous mid operation. So the optical cavity of the laser, it has a plane that is along with a high reflecting mirror at one end and a concave output coupler mirror of approximately 1% transmission at the other end. The two mirrors and the active mixture like it tells. So this is the working of the helium neon laser. You can see that it is pumped to all the energy states and then it is transmitted to the lower energy states as well. So when the voltage is applied to the electrodes, it ionizes the gas. The electrons and ions thus produced are accelerated towards the anode and cathode respectively. So the electrons they acquire a higher velocity due to the smaller mass when compared to the others, transferring the kinetic energy of helium atoms through an inelastic collision. So thus the helium atoms, they are excited to an F2 and F3 state because of its light mass, and F2 lies at 19.81 electron volt, F3 at 20.61 electron volt. So these are metastable states in this case, and therefore they cannot return to the ground state by spontaneous emission. Rather, they return by transferring the energy to the neon atoms that have identical energy. This is known as resonant transfer of energy. Now the neon energy levels E6 and E4 nearly coincide with the F3 and F2 of helium, so that the resonant transfer can occur. So the additional energy 0.05 electron volt is provided by the kinetic energy of the helium atom. And it is only because of the near proximity of these energy levels that the energy exchange occurs with a high probability, so that population inversion is fulfilled. So there are three main transitions that are important to know. The first is E6 to E3, that is a laser beam that generated that is red in color at a wavelength of 6328 angstrom. Now as we know, 1 angstrom is 10 to the power minus 10 meter. Second is E4 to E3, where it produces an infrared beam at a wavelength of 1.15 micrometer. And finally, we have E6 to E3, which produces a light in the far infrared region at 3.39 micrometer. Now, the application of helium neon lasers. Now, we have seen it before because it is present in supermarkets to read the barcodes. The red light that we see of it, or the green light, or basically the light that we see that is shining on a barcode to scan, is nothing but a helium neon laser. It is also used in holography in producing the 3D images of objects. And it has many industrial and scientific uses and are often used in laboratory demonstrations of optics. Second is the carbon dioxide laser. It was the first successful molecular gas laser produced in 1964 by C.K. and Patel. And in this case, the transitions that occur between the different vibrational levels helps in the laser effect in CO2 lasers. CO2 has a linear structure with a carbon atom present at the center. So we have two oxygen atoms and together is connected by a single carbon atom. Now, there are three different modes of vibration that is possible because of this. The first is a symmetric stretching mode. The second is a bending mode, and the third is asymmetric stretching mode. The symmetric stretching mode refers to the carbon atom basically remaining still and the oxygen atoms moving around about its axis, vibrating about the axis here, front and back, as we can see, left or right. The second is the bending mode, where the oxygen and carbon atoms would vibrate at right angles to the line passing through the center of gravity. The third is asymmetric stretching mode, where they vibrate asymmetrically or opposite to each other. So like if an oxygen atom is vibrating like this, and it comes here, the carbon atom would oppositely come here. And therefore they are not in unison. Otherwise it would be the same thing as symmetric stretching mode. Now, carbon dioxide lasers contain a discharge tube of a diameter 2.5 centimeter and a length of 5 meters. So it is a very long discharge tube. It is filled with a mixture of carbon dioxide, nitrogen and helium in a ratio of 1:2:3 atomic proportion. The discharge is produced by DC excitation and the active centers here in this case are the carbon dioxide molecules. Now here the CO2 laser works in a similar way to the helium neon laser, where nitrogen plays the same role of helium here, where it goes to the excited state by colliding with the electrons, which then transfers energy to the CO2 molecules, which eventually gets excited and it passes it on, so on and so forth. The lowest vibrational level of N2 has nearly as much energy as the asymmetric stretching mode of CO2 molecules. And so the excited N2 readily transfer energy to CO2 in resonant collisions. But another factor that plays an important role here would be operating temperature, which helps in determining the power of the laser. Now there are certain good things and bad things about this laser, or better to say advantages and disadvantages. The advantages are it has a very high power, it depends on the operating temperature, the power, and the power can also be determined by increasing the length of the gas tube. But the problem is the CO2 molecules will eventually dissociate to form CO, and which might end up contaminating the active medium. So therefore, using a vacuum pump, we have to occasionally remove the carbon monoxide from the active medium. Finally, we have its applications known where it is used in drilling, cutting, etching, and welding, and it is used in open air communicators. It is also used in pollution monitoring and remote sensing, in the medical field for microsurgery and bloodless surgery. Lastly, we have the ND-YAG laser, which an example of which is the Ruby laser, developed by T.H. Mayman in 1960. Now, ND stands for neodymium, and Y here is yttrium, A is aluminum, and G is garnet. So it is a neodymium laser doped with yttrium, aluminum, garnet, Y3Al5O13. This is the most popular type of solid state laser, where in this case the yttrium ions in the YAG crystal are partially replaced by the ND crystals or ND ions. The crystal atoms in this case will not participate in the lasing action, but rather they serve as a host lattice where the active centers will be found. So the ND-YAG laser is made of elliptical cylindrical reflectors, where one end is fixed with a focus of krypton lamp acting as a pumping device. The other focus is silvered, where the flash on the krypton lamp will, after reflection, will be placed at the other end. And the ends of the laser is also polished with silver so that resonance can be achieved. We then have the working, where it is similar. It is done by optical pumping, which excites the ND ions from the ground state to higher states by absorbing a certain wavelength, in this case 800 nanometer and 730 nanometer respectively. So the transition is then takes place from a higher state in E4 to a level in E3, which is non-radiative. E3 here acts as a metastable state, and then the population inversion is achieved between the metastable states of E3 and E2 after continuous excitation. So any spontaneous emitted photon will make the already excited neodymium ions to undergo transition between E3 to E2 that produces coherent stimulated photons, and it yields a laser beam of wavelength 1064 nanometer. And then it makes a transition from E2 to E1, which is a non-radiative state, or in other words, back to the ground state. Finally, we have its applications, where it is like the carbon dioxide laser. It is also used in drilling, cutting, etching, welding, and surface hardening. It is also used in the military for range finding and target destination, along in the medical field for surgeries for cataracts, gallbladders, and treating gastrointestinal bleeding. So with that, we come to the end of this presentation and this topic. I hope all of you have understood this topic well, and it might be useful for you in the future. I hope I have cleared the concepts well as well. Once again, thank you and have a good day.